Welcome to the course on two-dimensional signal processing, principles and practices. In this lecture, we'll see the fundamentals of 1D signals a little more, that after completing that even and odd signals of periodic signals also. The periodic and aperiodic signals, we had given the definition in the previous lecture. For example, what are the few periodic and aperiodic sequences? How do we get their fundamental period? So, as we said that for the periodicity, x of n should be equal to x of n plus capital N for all n values, and n is the equation which is satisfied for the minimum value of n, capital N, that n is going to be the fundamental period. So, if we take the two periodic sequences, suppose we add the two sequences, periodic sequences, and the resultant signal would also be periodic. So that's what the sum of two or more periodic sequences, not only two, more periodic sequences, it would also result in periodic sequence, and it will have a fundamental period. And for example, if x1n and x2n, there are two periodic sequences with the fundamental period, x1n has the fundamental period capital N1, and there's a second one which has the fundamental period N2. In that case, the sequence will y of n, if we add the two, will also be periodic with a fundamental period n. That n which is given by the fundamental period of the two sequences x1 and x2 adding together would be n1 n2 by GCD of n1 n2, where that is n1 is the fundamental period of the first signal and n2 is the fundamental period of the second signal, and the n1 and n2, they multiply them, and GCD of this n1 and n2, we take the greatest common divisor of these two, which gives the fundamental period of the resultant signal. So this is how we can find the fundamental period for the sum of two or more periodic sequences. So now we'll take some examples of the periodic and aperiodic sequences, find the fundamental period. But for this case, that we will take x of n is going to be cos of n pi by 4, which is periodic or not, need to find out. If so, if it is periodic, and find this fundamental period. So what is we have to find first omega n, that is what is the value which is to be satisfied with 2 pi by m, where 2 pi by or omega by 2 pi, it's going to be m by n, the ratio. It should be rational number for periodicity. So for this signal, if we take, that is omega is pi by 4, this is going to be omega, and by this omega this is omega, what we had taken from here, and n is in this equation, substitute it here, 2 pi by m. So omega by 2 pi, which is going to be, this is omega by 2 pi, it's equal to m by n, the ratio, which is going to be, the pi and pi get cancelled, this is going to be 1 by 8. So 1 by 8 is this ratio. So that's what we had given here, 1 by 8 is this ratio, and this is the ratio of integers 1 and 8. So this is a rational number. So m by n ratio is a rational number, and the fundamental period is simply the 8. So this signal is periodic and with the fundamental period 8. So this is the way in which we can find the fundamental period of a discrete sequence. We take as example 2, in which that whether x of n equal to cos 2n is periodic or not. If it is periodic, again find the fundamental period. So we'll go to the omega n equal to 2 pi m. This is the equation which we had seen. And what is omega? We find it here. That is going to be 2 in this equation, the example given. And find this 2 into n, which is equal to 2 pi m, where omega by 2 pi, what is that? 2 by 2 pi, it's equal to m by n ratio. As we say, this ratio is 1 by pi, which is not a rational number, or which is not the ratio of integers. So it's not a rational number here, 1 by pi. So this signal is aperiodic. So simply we can say that if you plot this signal with respect to n, and you can observe that it won't be having the pattern repeating. So this is an aperiodic sequence. So for example 3, we take the signal which is x of n equal to minus 1 per n. So if such type of signal, first you can just to visualize that x of n, which is an n, you can plot this sequence and see that is there any repetition in the sequence. So you can see this pattern, suppose if from n and 1, 0 and 1, this is repeating, this pattern is repeating. So immediately you can say this is periodic. And what is the fundamental period? How many samples to which it is repeating? So this is 2, n equal to clearly seen from the picture, that is n equal to 2. So if you plot this sequence, another thing can also be observed. It is going to be alternating in sign. So one is plus and minus, plus minus, and so on. So you can see that, and the pattern is repeated for every 2 samples. So now we take this, this is a periodicity n equal to 2, and this signal also can be written as x of n equal to cos pi n. So this equation obeys the same pattern. So cos pi n and x of n equal to cos pi n. So if you omega n equal to 2 pi m. So if now you know the equation of this signal. So now omega by 2 pi is the m by raise omega is pi. What is omega by 2 pi? You can find out, that is here omega by 2 pi is pi by 2 pi, which is m by n, the ratio, and this is going to be 1 by 2, the integer ratios. Two of them are integers, so this is going to be a rational number, and this is a periodic sequence of n equal to 2, as we have seen in the picture itself. After every 2 samples it is repeating, so it's a periodic sequence. Now we come to the third category, that is periodic and aperiodic. So we have seen even and odd sequence, and the periodic and aperiodic sequence, and the energy and power signal. So there is a case in which the signal energy and signal power plays a role in the Fourier analysis of 1D and 2D as well. So we'll see the relation between this coefficients and then the signal. So this signal is taken x1 of t, which is defined as from -1 to 0, this amplitude is 2, and it is exponentially decaying 2 e power minus t by 2 after t greater than 0, greater than or equal to 0. So if you take this sequence, you can observe there are few things from this signal. One is, as t tending to infinity, the signal amplitude goes to 0. Okay, so this is an exponentially decaying sequence. This is one observation, and we also, for that such type of signal, we can say the signal which we have, it's an immediately you can have this. This is also not a pattern repeating. This is only one pattern here. This is an aperiodic signal. We can straight away conclude from the image or the signal here. And so the energy, if we calculate, energy is how do we calculate it? This is x square t dt. So that's formula to find out the energy of a signal. So from minus infinity integration, minus infinity to plus infinity, x square t dt. So x of t is here for defined in different ways from the different intervals. So -1 to 0, it is 2. So your integration is separated into two components. One is from -1 to 0, this signal is given 2. So x of t is 2 square dt, and then from 0 to t, it is different exponential decaying sequence where 2 e power minus t by 2 square x of t square dt. So x square, the signal square, is giving the energy. So this integration results in 4t, and you apply the limits, and similarly 0 to infinity you get the 4, so you get the 8. So finite value. So this has a finite energy. So this signal has a finite energy, and then so that's an energy signal. So if you have the finite energy, and then in the case of power signal, let's see the power signal. So in the case here, power signal, it is repeating. You can see the periodicity, a pattern is repeating over here in the negative time index as well. x2 of t, it's a function of t, and 0, 1, 2, 3 are the points it is crossing the time. It is t0 here, the y is crossing 0, these points. So there is a pattern. Okay, so if you see that, this amplitude is going to 0 when t is tending to infinity? No, it doesn't go to 0. Okay, anyway, this is repeating. This pattern is going to be this side, minus infinity to plus infinity, this would be repeating. So this is a periodic signal. So this periodic signal are the power signal. So how do we find out this power of the signal? So whether it has a finite power or finite energy. Okay, so this power is 1 by t. Take a one cycle of it, 1 by t minus t by 2 to plus t by 2 here. Okay, and x square t dt. So if we integrate it, x square t 1 by 2 minus 1, and here it is going to be plus 1 here, t square. So this is t. Okay, the slope is t here because it is 1 and minus 1. At 1 it is going to be 1. So it's simply t. So t square dt, it results in 1 by 3. So in this equation, the power of this particular signal results in 1 by 3. It's a periodic signal. So the observation is it doesn't go to 0 as t tending to infinity, and this is also a periodic signal. So immediately you can start finding the power of this signals. That's going to be 1/3. And we can also find the RMS value, root mean square value, from the power of this signal. So that is the signal power is equal to the square of its RMS value, in which the RMS value of the signal is 1/√3. So that's it's a square, the square of RMS value. This, if you square it, 1/√3, and this is going to be the power. So if we take the root of it, so that's giving the RMS value of the signal. So we can find the power. This is finite in power. The signal has a finite power, and the previous signal which has a finite energy. So this is how you can find out whether the signal is energy or power. So finite energy it has, or finite power it has. So generally the aperiodic sequences are energy signals. You can find the finite energy, and the periodic signals are power signals. You can find the finite power. And also root mean square value of the signal also can be identified from the by taking the power. So the power signal has a certain few more classifications as well. So if a signal is periodic signal, simply for example x of t, see this cosine or sinusoidal signals can be taken. How the power calculation is helping in finding the amplitude, how it is related to this amplitude. Suppose x of t is equal to c cos omega naught t plus theta. So c is the amplitude here, and omega naught is the frequency, and theta is the phase, initial phase which it has. So if we calculate the power of this is going to be a periodic signal again. So in that case you can calculate the power. Power is limit t tending to infinity 1/t minus t/2 to plus t/2 x square t dt. So when we apply this minus t/2 to plus t/2, so just replace this with x square t, that is c cos omega naught t plus theta the whole square dt. So the resultant would be, you just do this integration, that 1 plus cos 2 omega t/2. So replace it and perform the integration, that would result in p equal to c square by 2, which is only depending on c. Okay, so the amplitude c square by 2, and what is the RMS value, which is root of this, isn't it, square root of this, the power. So the value x of t is root of the c by root 2. So you can see the value is that peak value, or the c by root 2 is the RMS value by calculating the power. So what is the power of this signal p is c square by 2. So these are the relation we need to know for the signals. If it is periodic, it has only one frequency. For example, if we have the signal which is of two sinusoids, sum of two sinusoids. For example, this is c1 cos omega 1 t plus theta 1 and c2 cos omega 2 t plus theta 2. So that x of t is having two sinusoidal signals, and this is continuous in time and continuous in amplitude. Okay, so just to understand the energy and power, we are doing it in the continuous in time and continuous in amplitude. Whereas omega 1 and omega 2 is not equal, so these two frequencies are not equal. So these two are two different frequencies and two different phase and two different amplitudes. Okay, so in that case, similarly we will find out the power. So p is equal to limit 1/t minus t by, that is take one period of the signal and integrate it, x square t dt. So this is going to be resulting in the sequence. Actually, if we take this x square t, the whole thing we have to take c1 cos omega 1 t plus theta 1 plus c2 omega 2 theta 2 the whole square dt. Okay, so each one can be written as like 1 plus 2 cos omega 2t by 2, and this also, and integrate it, substitute the limits, you would get for the first case, or you can extend the argument of the first one. The first sinusoid would give the c1 square by 2 and the amplitude square by 2, and the second one would give the c2 square by 2. Okay, so the same argument can be applicable here as well if we have the two different sinusoids of different frequency. What is the value of this? Okay, so root of the whole thing, c1 square plus c2 square by 2 root. So this is the RMS value of the sum of two sinusoids. So we can find out the RMS value of also the power of this signal. So if we take the category, that is another category of sum of two sinusoids, in which this omega 1 and omega 2 are equal. That means two of them have the same frequencies. Okay, so c1 and c2 will have the different amplitudes, and we add up together. So in that case, theta 1 and theta 2 also different initial phase, but frequency is same. Okay, so in that case, if we find the power, still it is periodic. So the p is, if you resultant integration would give C1 square C2 square plus 2 C1 C2 cos theta 1 theta 2 by 2. So if we add this, square this one and take the individual component, the integration, apply the limits here and then get this P. So now the idea is to how these are related, the power and C1 and C2 are related. That is important for the power signal. So here RMS value of x of t is C1 square C2 square to C1 C2, root of that is the RMS value. So RMS value can be found from here, C1 C2 different amplitudes, different phase, but same frequency. Okay, so in that it's not only it's not only depending on amplitude as in the case of different frequencies, but it is also depending on the phase, which is different, and the cosine of that. So this is about the energy and power signal. So if we have the power signal which is having the number of sinusoids, that means n number of sinusoids, they summed up together with distinct frequency. This omega n1 frequency, omega 1 and omega 2 are not equal, or any other frequency of n is not equal. That is sum of these sinusoids, n equal to 1 to infinity x of t, Cn cos omega n t plus theta n. So in this case, omega n is omega 1, omega 2, omega 3, and n is varying from 1 to infinity, as many sinusoids you have. In this case, what is the power of this? Okay, P is equal to 1 by 2, n equal to 1 to infinity Cn square. So because this every sinusoid is going to result in the amplitude, suppose for C1 square by 2, and next one C2 square by 2, C3 square by 2, and C4 square by 2, and so on, and add up all of them. That is indicated by the summation. So it's only the C1 square, Cn square. So this Cn square is the amplitude of this sinusoid, which gives the power, and we can also find the RMS value of this here, which is going to be root of this thing, RMS value. If you want all the sinusoids, this would be going to be the summation of this, and root of that would be the RMS value. Now we get into this, if the sinusoid has a DC term. So far we had checked the power of the signal or RMS value if it does not have the DC here. Okay, so the DC is the C naught here. If this signal has DC, so how this DC is going to affect this power of this signal? So power is simply here C naught square. So this would be adding to the power. So this coefficient, we can say that the C naught is DC term is the amplitude square is the power, plus for each sinusoid you have the C1 squared by 2, C2 squared by 2, and so on. So for each square where omega n is distinct, okay, it's all distinct. In that case 1 by 2, n is varying from 1 to infinity Cn square. So this is the power, and if you take that Rm here, this would be only the power case. So if the signal for a complex sinusoids, so if x of t is not simply cos or real cos or the sinusoidal signal, so this is having the amplitude d e power j omega naught t, or there is a complex frequency omega naught. So if this is the exponential sequence, then what is the power? How do you compute that? So t varying here minus t by 2 to plus t by 2, and the limit of t infinity going to t equal to infinity 1 by t, and d e power j omega naught t the whole square dt. So this is xt square now. So the magnitude squared. So this part would result in 1, right? So d square dt integrating it would result in here, this is 1, we're going to be 1 p equal to simply d square. So by substituting the limits, it's going to be only the amplitude of this. The power is going to be only the amplitude, that is d square. So the RMS value would be root of that, which is only d. So complex signal which has one amplitude, the power is only depending on the amplitude, d square. So the classification even and odd signal, and the periodic and aperiodic signal, and the power and energy signals, these are the major classifications we have seen. Now the signal models, what are the signal models we have in general in the signal processing, so that we can use these models and make the mathematical expression of the signal, so which is captured in real time. So we can always express the signal with these models. Okay, so let's take this first one is the unit impulse function. So we know that del of t, and that is in continuous time, and in discrete sequence it is del of n, which is defined at n equal to 0, here t equal to 0 only, and that is one signal, basic signal model. And unit step function or the sequence. Okay, so when it is continuous it is called the function, when it is discrete it is called a sequence. So this is u of t, the signal, and the or u of n, it's going to be a step sequence. So this is the second model, and the third one is a ramp function or the ramp sequence, t u of t or n u of n. This u of t is multiplied with the t time or n here. And similar, the fourth one is parabolic function or a sequence. So it's t square by 2 u of t or n square by 2 u of n. This is another basic model. Also the sinusoidal function, sin omega t or sin omega n, these are also a basic signal models, or cos omega t or cos omega n. So that can be written in terms of sine. Okay, so here, and then exponential one, exponential function e power sigma plus j omega t. So this can be written as e power sigma t e power j omega t, or we can represent it as capital A alpha power n. So this alpha can be e power sigma plus j omega. So this way, another basic model is an exponential function can be defined also. So these are the 6 categories in which basic model signal model is defined, and we'll use these models to define the signal, develop the mathematical equation of them. So further getting into this, how to visualize the signal models, you have the t and del of t. This is the impulse, and it depends on the amplitude. The impulse would be of high amplitude. If you say this is 1, that is going to be unit impulse, and the step signal t, which is defined at t equal to 0 as 1 and greater than 0 also as 1, that is a step signal. And this is a Dirac delta, where it is minus epsilon by 2 to plus epsilon by 2, this is having 1 by epsilon. So this is also equivalent to the function which is given here. And exponential decaying function, as we have seen, e power minus at and u of t, this is multiplied with this u of t. That means u of t is defined only after t greater than or equal to 0. So e power minus at is defined only for positive values of t greater than or equal to 0. Whatever the signal you multiply with the u of t, then that becomes a signal which is defined only after t greater than or equal to 0. So now if we take e power sigma plus j omega t. So for example, in this case, this is neglecting this part, e power j omega t part, because it has e power sigma t, d power j omega t. So taking only this one. So where omega part is neglected, and only if we have this sigma equal to 0, then this part becomes 1. So that's where this line is plotted, this sigma equal to 0. This gives, for t any value, is going to be simply a constant value, that is here 1. Okay, and if sigma is greater than 0, so that would be exponentially increasing. Okay, and if sigma is less than 0, then it is exponentially decaying sequence. So these are the sequence, you can get it from the exponential function as well. So suppose we include this part as well. So sigma equal to 0 total, if we take sigma equal to 0, only this has some omega, then you have the oscillatory signal. So this can be a cos, this is going to be cos omega t plus j sin omega t. So this function you can have e power j omega t, from that you can have the oscillatory sequence. If sigma is less than 0, so this becomes less than 0, this magnitude actually in omega equal to 0, this magnitude is constant. Whatever the value sigma was, sigma is equal to 0, that is going to be unity. And if sigma is less than 0, that is again this is multiplied with the cosine or sine sequence, so it's going to be a decaying sequence. That's a damping sequence actually, the signal is damping. So this would damp the signal, it will decay. And if sigma is greater than 0, so it would also increase the amplitude, which has the oscillatory response as well, but the sigma is greater than 0, so it would increase the amplitude. So you can have both of this in this case. So it has a frequency and it has a signal which is increasing amplitude e power sigma. So these are basic signal models, we would use them in the development of them. Now we come to the sampling part. So how do we understand the sampling? So if any signal which needs to be used in the DSP or FPGAs needs to be converted into digital signal. So the analog signal needs to be sampled first. That's the first step of any processing DSP. What do we understand from this sampling? So okay, yes, it is collected at regular intervals. How do we fix the time, and what is the actual process in the sampling? So if we take the signal, suppose t, and the x-axis is t and xa of t, and this signal is given over here. This is the analog signal, and this signal, if we sample it at an appropriate value, this is 1, 3 and 5, and there is a time interval involved. So we get some sequence here. This is x of n. You can see the changes in it. So xa of t is now made x of n. How this t is now replaced with nt. Okay, t is the sampling interval and n is this integer. Okay, now what do we do actually in this case? So if we take xa of t, assume this sampling or the sampler as a switch. Okay, so that switch, you just on the switch and off switch, off, on and off at a regular interval. So if you just take this, data is coming in, you switch on, then you would get this sample, and it is switched off, and this is the time which it is off, and then it is on for some time, you get this signal, and then off, and so on. So this regular interval for which you are collecting the sample t, for which it is off. Okay, so that is the sampling time. So we get what is x star of t. So how do we define this expression? Actually, x star of t is that if it is sampler gives, suppose x star of t, that is switching on and off time. So we can take this operation as a impulse modulation. That means any signal, this xa of t, the analog signal, is multiplied with the impulse signal that is having a time period t, capital T, and multiply them. So you get the output, which is the impulse modulated output. This signal is impulse modulated. So x star of, which is x star of t, xa of t, del of t, t. Okay, so this is a signal xa of t, and you just multiply it with an impulse at a regular, this has an interval t. So that's called impulse modulation. So if you do the xa of t, the impulse modulation, you can see that this is going to be an impulse at these points. Okay, so you get for one impulse, 2, 3, 4 and so on. That impulse is having the unit amplitude, because you are multiplying with xa of t. What was the amplitude of this xa of t is multiplied, and you get this impulse amplitude as signal amplitude at that point when you are closing the switch itself. So this is x star of t. So the impulse modulated sequence, we can say this is impulse modulated sequence of xa of t. So from this, visualize this, suppose this is x of t and impulse modulation or the impulse signal, and multiply these two, you get the impulse modulated sequence here. Okay, so this is the impulse modulator, just to visualize the impulse modulation output. At the time interval involved is 2 t, and every interval is t. Okay, so the same thing if you look at that in the frequency domain. So this x of t, what we have, it has a band, it's a band limited signal. First of all, to sample it, it should be band limited, then you know the maximum bandwidth of the signal. So if it is not band limited, first you need to pass it through an anti-aliasing filter and band limit it before applying to the sampler. Okay, so the sampling theorem is valid only for this one is the band limiting, otherwise it would create an aliasing. And so the x of 0, this is x of omega here. Okay, so this is a spectrum of the signal xa of t, what we had here. This is x of t or xa of t, and this is the spectrum, that is omega by 2 pi, and it's the impulse signal whose spectrum, that impulse train what we had here, the impulse train whose spectrum is this. This is del omega, and it has a t, and in the spectrum you have the fs, that is a sample, the time fs, and then there you are multiplying that impulse modulation. And if you do this convolution of this, so what we have is the spectrum, the one spectrum of the x of t or xa of t is getting repeated due to the sampling. So this is the discretization process. When you discretize a signal in the time domain, in the frequency domain, the baseband or the spectrum of this particular one gets repeated. Okay, so the discrete signal will have the repetition or the periodic spectrum. So this is centered at Fs, and this is at 0, and this is centered at 2 Fs, and this is minus Fs, and here is minus 2 Fs. Okay, so this is the discretized or the sampled signal will have the spectrum like that. Now this is about the sampling. So that is nothing, sampling is nothing but a impulse modulation. Okay, so we do the impulse modulation to get the discrete signal. So the discrete signal spectrum is getting repeated, or it becomes periodic when you discretize that signal. Now coming to the signal operation. So the signal operation, what are the basic operations possible in the continuous time and discrete time sequence? One is operation. One is time shifting. You can shift it right or shift it left. For example, or the scaling. The time base can be compressed or expanded. So that, or the time reversal, like flipping x of t equal to x of, make it x of minus t. So these are three different operations, and combine all these three. Okay, so combined operations are also possible with this. So what are the ways in which we can do it, and what is the resultant visualization of the signal? So can be checked here. So for time shifting in the continuous time signals, the signal is x of t, in which you have the time shifted signal. How do we get x of t minus t? Okay, so where t is the positive number and it is right shifted, the signal is right shifted, then it is going to be x of t minus t. If that is left shifted, that is this t is negative here, so it's left shifted, x of t plus t. So these are the operation performed on this x of t. It can be right shifted or the left shifted, shifting delaying in the right side or in the left side. So let's see the signal x of t, that is continuous in time, continuous in amplitude here as well. So we have taken 0 to 16 here, and x of t is this. Define some amplitudes, a random signal in which that it is 0 for some time, and then there is a slope here, and it's 0 or 3 for some value, and there is a slope, and 2, and then it is going on. So if we shift this signal here, x of t minus 2, I want to shift it by 2, and then right shift here, that is going to be 5 here. Instead of starting from 0, it is starting from 2. Okay, so there is a 2 time shifts available, and the whole thing, no other amplitudes are changed, only the time is just delayed. Instead of starting from 0, it is starting from 2. That's it. So the shape and everything is preserved here. And the time shifted t equal to 2, positive number, and this is a right shift. Okay, and if this is going to be left shifted, okay, instead of 0, so what we can have is that t plus 2, so x of t shifted here, so it is going to 0. Here you can see x of t equal to x of t minus t, where it is t minus 2, t is negative, that is a left shift. This is a left shifted signal. So you can have the signal x of t, and it is left shifted, so it is this 3, it would go to 1, it is 1 here, so it is left shifted. And the remaining time and the other things, the amplitude and everything is preserved here. Okay, this is t minus 2 and t plus 2. So now coming to the flipping operation, just how do we get the mirror image of this? For example, the signal f of t is this 0 here, minus 1, minus 3, minus 5, x of t or f of t is e power t by 2, that's exponentially increasing signal, and if you flip it, the t is made minus t here, so you get this t becomes plus t over here. So it's a mirror image, e power minus t by 2. This is exponentially decaying sequence instead of increasing sequence. So that's just a flipping sequence. So the flipping sequence is required to do some operation while doing the signal processing. So this is called flipping, making x of t equal to x of minus t. So the amplitude also is reversed here, because amplitude involves this t, it's a function of t here. In discrete, we take this same example with a discrete sequence x of n, and how do we take the time shifting? So x of n minus n, it is going to be a right shift where n is positive here, and if it is left shift, n is negative, it's a x of n plus n. So this sequence, same sequence we'll take, but we have discretized it. It is defined only at some points, that is integer value of n only. So these are zeros, and 1, 2, 3, and then 2 here, 1, and same. So this is a sequence, this is x of n. So if right shifted x of n minus 2, instead of 0, it is starting from 2. Okay, so the sequence, and the remaining, this is at 6, this was at 4, right. So 4, it is delayed by 2 time units. So time here is n equal to 2. So the remaining things are preserved. So it's just a delay by 2 samples. Okay. And if you make this right shift, the cases here x of n plus 2, left shifting would 0, 1, 2, 3, and so it would be -1 and -2. So 2 samples here, it is shifted left. Okay, so the one which is at 16 would be at 14. So just advancing 2 time units. Okay, x of n plus 2. So x of n minus n, where n equal to -2. So that would be n plus 2. Okay, so this is left shifting. In the sequence, it is number of samples. It is very clear that how many samples you would be delaying or advancing. So next, after shifting, you do the scaling of the continuous time scaling. So that means you adjust the time base of it. So if a signal is x of t and scaled by a factor, that means the x of t is multiplied with a. This a can be greater than 1 or less than 1. So let us see, if it is greater than 1, that scaling result in the signal, which is the basis, result in compression. Suppose x of t is made x of 2t, it is compressed, the time scale is compressed. If a is less than 1, that means half t, x of t is made x of t by 2, then it is making the time base expansion. So this scaling would result in, depends on the value which you use for scaling. It can be greater than 1 or less than 1. If it is greater than 1, it would result in compression, otherwise it would result in expansion. Let us see in the same example. This is x of t, and where greater than 1, x of at. So here we have made also x of at, here it is a is less than 1. You can see the expansion and the compression here. So where it is 3 and it is made it 1.5, 2 times here it is compressed, and this is 2 times expanded. This base is expanded. You can see x of at, which is expanded, and here is the a is less than 1, which is made t by 2, and here it is 2t. That's base time compression, and expansion can be viewed here. In case of discrete sequence, where signal x of n is this, and time scale again, how do we compare it with continuous one? So a, here n is defined only at integer values. So multiply by a. A is again greater than 1, it is going to be a compression, and if a is less than 1, it is going to be a expansion. Okay, so a can be 2n, it can be less than 1, it is 0.5 n, and so on. So when we do that such operation, you will lose the data in this case. Okay, so for example, you can take the signal x of n, that's the same signal, and we have 0, 2, 3, 4, 5, 6, 7, 8. So this is 2n, and if we take n by 2 for the sequence what we had considered earlier, this is a greater than 1 and this is a less than 1. Okay, so here you can see intermediate points are made become 0. So some of the values are not defined at all. So 0, 1 is there, and here it is 0, 2 in between. These values are 0. So between 8 and 10, this is 0. These values are 0. Okay, so n by 2 would lose the some of the information in this case. So when we do the scaling in the discrete, generally these two, there is an interpolator used after this operation, which can be made these 2 points and then add it and make an average of this and fill this gap if it is an integer value. So that is also possible to do the scaling operation. So time reversal is we have the x of t is made at x of minus t, that is a flipping sequence like already we had seen. That is, if it is x of t, you can see the t in minus index, okay, t equal to x of minus t. So you see the positive indexes become the -1. Also in discrete, how do we see that sequence? It's a flipped signal is here, the n has become minus, you can see here, and that is become negative indices x of minus n. That's a flipped sequence. So we can combine these operations as well, that is time shifting and scaling, also flipping the sequence. How do we do that? these three operations can be combined. Delay, shifting and scaling can be combined, and making the operation also. So what we have learned in this lecture is that, so the periodicity examples are periodic and aperiodic signal, and how do we compute the energy and power of a signal. So if it is aperiodic signal, that compute the finite energy, and if it's a periodic signal, it's going to make compute the finite power. Likewise, we can have this periodic signal also having the same frequencies, sum of two sinusoids or sum of n sinusoids, how the power of this signal is related with the amplitude, and getting the RMS values. We had and we have also seen the signal operations like time shifting and scaling, and for continuous domain and the discrete domain. Also, we had looked into some of the basic signal models, very popular ones, and these 1D signal models can be extended to 2D signal models as well, and these 2D signal models we can see in this course to use how to develop the two-dimensional signals and its processing as well. So we'll continue with the signal operations of the combined case of time shifting and scaling in the next lecture. Thank you.